In this video, we're going to go over the KutaSoftware Infinite Pre-Calculus free worksheet evaluating limits, and this is at removable discontinuities. So in number 1, we're going to be evaluating each limit. So the limit of f of x as x approaches 4, looking at the graph in number 1, as we approach 4 from the left direction, we're getting closer to 4 for y, and as we approach from the right, we also get closer to 4. However, at that point 4, when x is equivalent to 4, y is negative 1, but the limit of the function coming from both the left and right is equivalent to 4. So regardless of the fact that the value at that actual point is negative 1, the limit is 4. Moving on to number 2, we're looking at the limit as x approaches negative 4. So approaching negative 4 from the left, we're approaching this removable discontinuity, and approaching it from the right, we're approaching that same exact point. So even though the value at negative 4 does not exist because it is undefined, the limit does exist. So we're going to calculate that limit. And in order to calculate the limit, we need to plug negative 4 in for x. However, note, if we plug negative 4 in for x, we'll get negative 4 squared plus 5 times negative 4 plus 4 for the denominator, which would be positive 16 plus negative 20 plus 4, which would give us a 0. And we know we cannot divide by 0, therefore it would be undefined. So we're going to need to simplify this first and then plug in negative 4. And in order to do that, we're going to have to factor this denominator. So we'll need to see what two numbers multiply to give us positive 4 and add to give us positive 5. And right away we can see that that will be 1 and 4. So writing the denominator factored, we'll have x plus 1 times x plus 4 for the denominator. So that's what's in the denominator, and in the numerator we have x plus 4. Now note, we can cancel out x plus 4 and x plus 4. So that will give us 1 over x plus 1. So by simplifying, we will now be able to plug in negative 4. So we're going to find the limit of 1 over x plus 1 as x approaches negative 4. So we'll take negative 4 and plug that in for x. So we'll have 1 over negative 4 plus 1, and you can see that we no longer have a 0 in our denominator, so that will be 1 over negative 4 plus 1, which is negative 3. So negative 1/3 is the limit as x approaches negative 4. So even though we do not have a value at that point, the limit does exist, and that's negative 1/3. Let's continue on to number 3. At number 3, we're still evaluating each limit, and it states the limit of f of x as x approaches negative 1, and it gives us that f of x is negative 1 when x does not equal negative 1, and it's 0 when x does equal negative 1. So we need to look at the piece of the function where x does not equal negative 1. That means that the function of x is negative 1 when x is less than negative 1 and when x is greater than negative 1. So as we're approaching from both the left and the right, our limit is negative 1. So negative 1 is our answer in number 3. So even though when we plug in negative 1 for x, we get 0 for f of negative 1, the limit is negative 1. Quickly, let's look at that visually. Here's our graph. We're at negative 1 for all points of x with the exclusion of negative 1. And at negative 1 in the x, we're at 0. So we have a removable discontinuity. However, like I stated, as we approach from the negative direction or negative side, and as we approach from the positive side, our limit is negative 1. Now for number 4, we're looking at the limit as x approaches 5. So we're looking at the first piece of this function for values when x does not equal 5. So that's when x is less than 5 and when x is greater than 5. So approaching from the left side and approaching from the right side. So what we'll do, we'll plug 5 in for that first piece. So we'll have negative 5 squared plus 10 times 5 minus 22. 5 squared is 25, and we're taking the opposite of that. So negative 25 plus 10 times 5 is 50 minus 22. Negative 25 plus 50 is a positive 25, and when we subtract 22, we'll get positive 3. So 3 is our solution in number 4. And if you want to double check, feel free to graph each of the pieces of this function, and you will see you have a removable discontinuity at x equals 5. If you look at when x equals 5, our y value is 2, however the limit, following the rest of the function, we get 3. Now on to number 5. We have the limit of x squared minus 4 over x minus 2 as x approaches 2. But look, if we plug in 2 for x, 2 minus 2 equals 0, so that will give us an undefined answer. So in order to find the limit, we need to simplify. So let's factor this top part. We need to see what two numbers multiply to give us 4, but add to give us 0, and that's going to be 2 and negative 2. So factoring the top, we'll have x plus 2 times x minus 2, and that's all over x minus 2. And if you want to double check your factored form, feel free to FOIL. X times x is x squared, x times negative 2 is negative 2x, and then we'll be adding that to 2 times x, which is 2x, but negative 2x plus 2x is 0, so we have x squared, and then we're going to be adding that to 2 times negative 2, which is negative 4, so x squared minus 4. Now you can see that x minus 2 will cancel out with x minus 2, so we're finding the limit of x plus 2 as x approaches 2. So we'll plug in that value of 2 for x to get 2 plus 2 equal to 4. So even though we have a removable discontinuity when x is equal to 2, because the function at 2 is undefined, we still have a limit of 4. And on to number 6, same thing. Plugging negative 3 in will result as 0 in our denominator. So we're going to need to simplify. And we'll simplify by factoring. So what two numbers multiply to give us 6 and add to give us 5? That's going to be 2 and 3. 2 times 3 is 6. 2 plus 3 is 5. So we'll have x plus 2 times x plus 3 in our denominator. And x plus 3 is still in our numerator. So you can see that I'll be able to cancel out an x plus 3. So now, as opposed to the limit of the entire function as x approaches negative 3, I'm going to find the limit of the simplified function, which is the limit of 1 over x plus 2 as x approaches negative 3. So plugging negative 3 in for x, I'll get 1 over negative 3 plus 2, which equals 1 over negative 1, which is equal to negative 1. That is my limit as x approaches negative 3. So even though at x equals negative 3, my function is undefined, we still have a limit of negative 1. Now on to our last question, the critical thinking question, number 7. In number 7, it says to give an example of a limit of a rational function where the limit at 3 exists, but the function is undefined at 3. So f of 3 is undefined. We need to find some denominator where if we plug in 3 for x, we get 0 for y. So let's just subtract 3. Then, if we plug in 3 for x, 3 minus 3 equals 0. So our denominator is x minus 3. So now we need to figure out the numerator. And it tells us that the function has a limit that exists at 3. So we need to be able to simplify this to where x minus 3 will cancel out in the denominator. So we're going to need to have x minus 3 in the numerator. And we want to multiply x minus 3 by some other, let's do x plus 3. So you can see that if we were to plug 3 in for x, we would indeed get 0 in the denominator, and the function at 3 would be undefined. However, the limit of x minus 3 times x plus 3 over x minus 3 as x approaches 3 does exist, because we can cancel out x minus 3 and x minus 3 to solve for the limit of x plus 3 as x approaches 3, which, plugging 3 in for x, we'll get 3 plus 3, which is 6. So we're going to be using this function, but this is the simplified form, so let's expand out that numerator. So x minus 3 times x plus 3 all over x minus 3. Foiling, we're going to do first, outside, inside, last. So x times x is x squared, x times 3 is 3x, negative 3 times x is negative 3x, so minus 3x, and then negative 3 times positive 3 is a negative 9, so minus 9. And when we simplify, 3x minus 3x is 0. And remember, that's all over x minus 3. So we'll get x squared minus 9 over x minus 3. But looking back at our directions, we're to give an example of a limit of a rational function. So we're going to need to say the limit of this rational function, x squared minus 9 over x minus 3 as x approaches 3. That's an example of a limit of a rational function where the limit at 3 exists, but the function is undefined at 3. And there's many other examples. As opposed to multiplying x minus 3 by x plus 3, we could have multiplied by x plus 2. Then we would have gotten, for our numerator, x squared minus x minus 6. So x squared minus x minus 6 over x minus 3 is also an example of a limit of a rational function where the limit at 3 exists, but the function is undefined at 3. And with that, we wrap up our limits at removable discontinuities worksheet. If you have any questions, please feel free to leave them in the comments below. And as always, don't forget to like, subscribe, and share.